Okay, so today we're going to study and prepare for Lab 6, Process Control Systems. Has to do with level measurement. And we're going to talk about different types of devices that can detect level in tanks. And then also we are going to go to the lab and concentrate on our pressure sensor level transmitter. It's a transducer transmitter combo. So that's what we're going to do today. We're going to go over a few little sections on Lab 6. We're going to spend about 15 minutes talking about this, and then we'll get ready to go on to the lab. So here we go. First, you want to put down a definition. Level is one of the most commonly measured processes that you will see in a process control system. We're going to go move on up. If you want to highlight these things on the table of contents, these are some, not all inclusive, but some of the things that we're going to do today. We're going to talk about objectives 1 through 7, and then I want you to go ahead and work skill number 1 in the lab this afternoon. And then, this is going to be Thursday, we are going to go ahead and do skill number 5. If you feel really anxious about finishing Lab 6, you can go ahead and finish skill 6 on Thursday. All right, so let's continue onward. Talk about the two parts of a level sensor. We have the transducer and the transmitter. Now, sometimes those transducers and the transmitters are combined in one piece. There are some outputs that have the transducer and the transmitter in two pieces. Now, the transducer is obviously the one that converts from one type of physical input out to another, which is electrical output. And then the transmitter is that which actually creates electrical output and sends it to the controller. In our case, on our lab equipment, the transducer and the transmitter are the exact same device incorporated in the same box. So we don't have to have two pieces. And this is an example of the pressure sensor that we have in the lab. Looks like this. It's a capacitive style where you have a flexible movement of a capacitor here. This is actually turned in the upside down position. As you notice, it says input pressure, which we know our tank is pressing downwards, and then the wires are coming out from the bottom. So if you reverse that, go upside down, you can be able to understand how this works. But the pressure pushes this flexible diaphragm towards the other plate. And as you know, capacitors is a building up of charge, and that is the way it is able to detect pressure. Now, another one where you have the transmitter separate from the transducer is like here in this flow example, where you have the paddle wheel, which gives us some kind of transducer from the flow of the water to the speed. It gives a pulse flow output, lets you know how fast it is. But this does not transmit it to the controller. You have to have a separate device, which is called the transmitter, to actually send it to the controller, and then it gives the analog current output of 4 to 20 milliamps. All right, moving on. Transmitters are designed in two types of analog signals, one being a DC voltage, the other being DC current. That's normally the case in all process controls. It's going to be in DC. It's not going to be in AC. Everything you're going to find at a nuclear plant when it comes to controlling is going to be in a DC mode. Another reason for that is during emergency situations, we may not be producing AC power. And because we're not producing AC power, we have what's called a DC battery backup downstairs. And all of the critical components and process control instruments will be using DC power only. Okay, so that chart was given an example of DC voltage output. In this particular case, it's showing a pressure indication with current output. So normally the current output's between 4 milliamps and 20 milliamps. Voltage output is usually between 1 and 10 volts. Okay, now we have a couple of different types of pressure indicators, level indicators. One's going to be using the use of pressure, one's electrical resistance, electrical capacitance, and then the ultrasonic one. The pressure one is like we had just been talking about, sits at the bottom of the tank, senses the amount of pressure of the liquid in the tank, and then sends out the respective response out, being Forb equaling 0 and 20 milliamps being totally full. You're familiar with that one from the lab. The other one is electrical resistance. This is another type of measuring device. It uses resistance based on forcing this wire wounding up against a certain plate, and then the resistance that is formed by the water, the pressure of the water, actually gives the output of what the level measurement is. I want you to notice that resistance levels are often used to measure raw sewage. Wow, that's nice. Sludge, and also, how about this one? Gasoline levels. Pretty interesting. I don't know if I want to put a lot of current down in a gasoline tank, but nonetheless, there you go. The other one is the electrical capacitance. This is similar but not the same as the one that we use in the lab. Notice that the capacitance is based on this probe and the edge of the tank. Well, if you're going to have capacitance between the probe and the edge of the tank, obviously it's got to be close enough to actually cause a capacitance value between the two, and then transmits the output from the top. Notice that the common application of this type of capacitance level is used with refrigerant, where it actually has to be connected very close to the pipe wall. Now here's the one we're going to be using probably, I think it's in lab 12, which is the ultrasonic. It's very interesting how this works, because the ultrasonic works by waves, usually sound waves, that bounce against the top level of the fluid and then returns and then is picked up by this ultrasonic level sensor at the very top. That particular one is used in it says ultrasonic sensors are used to measure a level of combustible fluids, because here you're using a sound wave or some other type of wave, and there's no actual contact with the fluid. And that's where the ultrasonic is actually taken into place. It's also be a good one if we were using it in a closed system. The next part of the section is objective number 4. Objective number 4 is talking about how to measure liquid in a tank based on the principles of pressure, that is pounds or force per square inch. We've already went over pretty much how that works. It starts describing how to do level measurement in an open container versus a closed container. Notice that in an open container you have to take into consideration the atmospheric pressure, which is 14.7 psia, and then you're able to add the hydrostatic head, which gives you the amount out by the pressure sensor itself. In a closed container, you don't necessarily have a consistent 14.7 atmospheric pressure on top of that container. You'll have some other type of air pressure, especially if you're increasing or decreasing the level of the tank and there's no way for the extra pressure to escape. In this particular case, you have to subtract out the pressure that's at the top of the tank from the pressure of the liquid that's below. The only problem with that is that this air pressure on the top of the tank may change over time or based on the level of the liquid. So what you have to do in this particular case is you have to put another pressure sensor up here at the top, which actually senses the pressure of the air or nitrogen or hydrogen, whatever is in that particular tank, and then measures the pressure of the liquid, subtracts the two out, and then sends that to the controller. So that's how you fix the situation in a closed tank scenario or a closed system scenario where you'd have to determine the pressure level in the tank. This is a good example of the accumulators in the containment building where we actually have a concentrated borated water volume, and then we have a 650 pounds of pressure above it, and this is actually nitrogen gas, and we maintain that pressure in emergency situations, because if the containment building, or like for example in a LOCA situation, and the RCS pressure reduces less than 650 pounds, these accumulators will dump directly into the reactor, so that we have a nice, great, big concentration of borated water that will fill the reactor totally up, so that we can maintain the fission process, or not maintain it, but reduce the fission process within the reactor vessel. All right, one of the last one is the bubbler system. Bubbler system uses actual bubbles. How about that? And it measures the pressure in which the bubbles have to be pushed out of the bubbler tube, and that particular pressure corresponds to the level of the tank. It's going to take less pressure to put it out when the tank is higher. More pressure when the tank is higher than less pressure when the tank is lower. That's how the bubbler system works. And now let's move on to the pressure sensor that we have on our laboratory. On the trainer that we have out in the lab, notice that this is the same type of pressure sensor. It has both the transmitter and the transducer included in this particular one. The pipe fitting here is what amounts to the bottom of the tank. Then inside there you have the two capacitive units, and then you have your electrical connection which goes to the controller. Moving on forward, I want to show you what's inside that pressure sensor. Inside there you have the circuitry for the transmitter. You have the flexible diaphragm here, and then you have a stationary electrode. And what it does is you have two oscillator circuits in this system. Even though it's not depicted completely, it does show you the diaphragm, flexible diaphragm. But the what it does is does a comparison between the flexible diaphragm and the stationary electrode. And what it does there is the oscillator circuit from the variable capacitance is compared to that which is of a fixed capacitance. Those two signals are subtracted, and then they compare it out, and then based on the fixed versus the variable gives you your output. And this is exactly how it's working. This particular transducer transmitter is working on the laboratory equipment out in the lab. I want you to make sure you highlight this paragraph. It's the paragraph right below figure 18. Gives a description of how that capacitive pressure sensor works, and then gives you an output, shows you get an idea of what the outputs are expected based on one operating properly. Notice that it says from 0 to 1, which is PSI, you should get somewhere between 4 and 20 milliamps as an example. All right, what I want to do next is I'm going to jump down to the lab itself, and make sure you could do your tag out, your lockout tag out, of course, and then also follow directions carefully. Make sure you do your circle slash, and then also make sure you do not leave before you have your lessons learned, and someone can designate someone in the laboratory as who is going to do the lessons learned on this particular lab. You're going to be working with the Honeywell process controller on this particular lab, and it's not very long, just a couple of pages. And so once you complete this lab, go ahead and fill out all the information and have it ready so you can begin again on Thursday. If you have extra time, you can move on and go ahead and go to Skill 5, which is a little bit further on down. Skill 5 is actually using, let me find it real quick. Nope. Just a moment. There it is. Skill 5. It's on page 45. Okay. Skill 5, you're going to be using the multimeter to test the pressure sensor. And we had done that previously before, where you do the hookups to the controller, and then you go ahead and set up your multimeter so you can measure the multimeter right out of the pressure sensor so you can get the accurate readings from there. If you wish to, go ahead and do Skill 1 and Skill 5. Okay, be sure to put your safety glasses on and treat Betty with respect. Thank you so much, and we'll talk to you soon.